Hello, BC Calc. This is going to be your day 63 notes. Today, we are taking a look at the length of a curve. So another application of integrals here is that you can actually use integrals to find the length of a curve over a certain interval, which is pretty cool. Before we get into that, we're going to be making some predictions in just a moment. This warm-up question says, determine the volume of the solid generated by taking the area bounded by this linear function and y equals e to the x, and rotating it around the x-axis. So what I want you to do before coming to class is, of course, try this one, but draw a good picture. And then I want you to think about the fact that we don't know how to integrate the function e to the x yet. So you definitely have to use the calculator in order to get the value for your definite integral. But once you've decided based on your picture if it's disk, washer, or shell, then from there, set up the appropriate integral, and because e to the x and that linear function are not going to have nice points of intersection necessarily, you're going to have to use that x stow a function and x store as b function. And x would represent the points of intersection of the left bound and the right bounds for your interval that you're integrating along. So I guess based on the way I've described it, I think dx is going to be the easiest case when revolving around the x-axis here. But if you want to use a different technique, certainly that's fine. But you have to do this to make sure that you have your bounds set and then use the calculator to calculate the value for your definite integral. So try that one based on my suggestions there. We are going to jump down to the bottom and it says make a prediction. So find the length of the curve y equals x squared from x equals 0 to x equals 1. And by the end of today, we'll be able to find this to 3 decimal place accuracy. So y equals x squared from 0 to 1 would look something like this. So we're trying to find the length of this curved part of y equals x squared. So in order to do that, and in order to make some predictions, I'll have you think about it for a moment, either hit pause or do something to think about how I can approximate that length at this point. And then I'm going to give you maybe 2 techniques that you might have considered. If you have another, you'll let me know next time I see you in class. Here are the 2 things that I came up with. So if we think about this curved part of y equals x squared, maybe we can compare it to what looks like a quarter of a circle and see if that's a decent approximation for the length of that curved part. So a quarter of a circle would be 1/4 of 2 pi r, a quarter of the circumference. And the circumference would be based on the radius of 1 here. So we wind up getting 2 pi over 4, which reduces to pi over 2. And pi over 2 is approximately 1.5 something. Let's see, pi divided by 2 is 1.570 or 0.571. So I would say if you came up with an approximation that's close to that to get started, then you're at least in the ballpark of the length of that part of the curve. I think that's a reasonable estimation. Another good estimation could be comparing it to this triangle right here, whose hypotenuse length we know, right? I mean, this is a 1 by 1. If you were to connect that chord right through on the curve, it would be a 45-45 triangle, so it'd be 1, 1, radical 2. So maybe radical 2 is a good approximation for the length there, which is actually pretty close to 1.57. It's 1.4. I think it's 1.4. Let's see, radical 2 is 1.414. So if you're somewhere in this range and you use a different technique, that's good. If you have that the length is 20.3, then you might have to go back and readjust some of your thoughts about this. So what we're going to do is now develop the concept of how do I use integrals to find the length of this curve along a defined interval. When you turn to the next page, you'll see some notation at the top. So notationally, you'll see that the length of a curve is denoted by capital L, and then from A to B would be denoted with those bounds of A and B there. Okay. So if a function is continuous and differentiable on an interval from A to B, we're going to divide AB into some sub-intervals there. And what you'll need to do is copy this picture into your notes. So take a moment to do that. If you need to hit pause, go ahead and do that as well. So what we're trying to do is find the length of this curve over this defined interval from A to B I've defined 2 points on the interval x sub I and then x sub I plus 1. And the length of the chord that connects those two x values would look like this red segment right here. So delta x is fixed along the way. Okay, our delta x, when we divide this into our n subintervals, delta x will always be that same fixed amount. But delta y is going to change based on the subinterval that we look at. Okay, so that delta y might be greater if we're looking at a subinterval over here, whereas it might be smaller if we're looking at a subinterval closer to A, let's say, just based on the inflection of this curve. So what are we going to consider? And I know the rest is sort of filled in on your page here, but consider x sub I and x sub I plus 1, that interval right there. What we know is that the length of that chord, if we use distance, is the square root of delta x squared plus delta y sub I squared. Okay. So that's the length of the red chord that I'm talking about in the picture. So then from there, we're going to do some fancy algebra here, and this is just to derive the general formula. This is not something I would necessarily think we would come up with on our own. But if you multiply by delta x squared on the inside over delta x squared, which is the same thing as multiplying by 1, well, what happens for the first term is that these two things cancel, right? You're just going to get that you're left with delta x squared here. And then from the second term, you can squeeze in the delta y sub I over delta x squared times another delta x squared. So this is just kind of cleaning some things up, right? Those two things cancel. Here, I'm just kind of pulling the delta x underneath here, writing it as that quantity squared times delta x squared. So then from there, what happens is if you factor out delta x squared from there, you get 1 plus delta y sub I over delta x squared times that delta x squared is the GCF that I factored out. And since we're writing this as a product now, the square root of delta x squared is just delta x on the outside. So do you see where we're heading with this? And I know this is on your page, but I'm slowly walking you through it here. So the length from A to B would be the approximate sum from I equals 1 to n of all such chords such that we take the square root of 1 plus delta y sub I over delta x squared times delta x. And when we apply a limit here, okay, so the last thing that you really have to write down there is if you take the limit as n goes to infinity for the sum of all such lengths, that's going to equal the length of the curve over this interval. And this turns into a definite integral from A to B. And what is delta y sub I over delta x? It's dy dx. So in order to find the length of a curve, it will actually be dependent on knowing the derivative of the function that we're finding the length along. So we're going to plug in that dy dx right here and actually square it according to our formula. Square root of 1 plus that derivative squared with respect to x. And of course, we'll get to a point where we do this with respect to y. But there is the derivation for the length of a curve. Okay, let's see if we can put it to practice then. So if you turn to the next page, it says find the exact length of the curve y equals x to the 3 halves from x equals 0 to x equals 5. If you graph x to the 3 halves on your calculator, you get a curve that looks somewhat polynomial-ish. Okay, x to the 1.5 power kind of has a similar type look to the way x squared would grow in functions of that form. So let's see, from 0 to 5, we're trying to find the length along that curve right there. So according to our formula, we need to find the length from 0 to 5, find the integral from 0 to 5 of the square root of 1 plus dy dx squared. Okay, so if y equals x to the 3 halves, dy dx would be 3 halves x to the 1/2 power. Right, so if we use our power rule there, thinking about finding the derivative, right, we're working back to derivatives, not antiderivatives yet. And then if I square that, that's what's going to have to go right here. Okay, so if you do dy dx squared, that would be squaring, that would be 9/4, and squaring technically radical x is just x. So we get 9/4 x. That's what's going to go right here, and dx. So evaluating this integral over the interval from 0 to 5 will represent the exact length. And we can do this relatively easily without a calculator if you do a quick u substitution. So let's let u equal the inside, because I know the derivative of a linear will just be a constant there. So that's going to be 9/4 dx. So to make things match with our du, we'll have to pull a 4/9 out in front of the integral. And now we just have radical u du. All right, so the antiderivative of radical u, if it's u to the 1/2, up it by 1, so now we're at u to the 3/2. Out front, you would divide by 3/2, so that's times 2/3. 4/9 times 2/3, u to the 3/2 power. Okay. And what are we integrating along? Well, you got to either plug 1 plus 9/4 x back in for u at this point, leave the original bounds, or if I've converted anyone to a u lover at this point, plug in the bounds for our u sub and get the bounds with respect to u. If I plug in 0, you get 1 plus 0, which is 1. If you plug in 5, you get 1 plus 45/4, which is, add 1 to that, 49/4. So maybe you don't like that as much. I'm not sure. Okay, but then if I multiply those constants out front, that's going to be 8/27. And let's see, when I plug this in for the lower bound, we're taking the square root of the upper bound first. So the square root of 49/4 is 7/2. So it's then 7/2 cubed. 7/2 cubed is 343/8. All right, that's what I get from plugging in the upper bound for u, minus the lower bound. Well, that's much easier. It's just 1. So when all is said and done, if you get a common denominator here, this becomes 335/8 on the inside times 335/8. And then the 8's cancel. So the exact length is 335/27 units long. So I think that's pretty incredible that we can use a definite integral to determine the length of a curve over a specified interval along the x-axis, or we might eventually be able to do this along the y-axis as well. Okay, so hopefully you followed that example along the way. Let's do another example where we're going to find the length of the curve x cubed over 3 plus 1/4x. But what I didn't do in this one, just because I forgot, I can't find the entire length. That would be tough to do. Let's go from x equals 1 to x equals 3. Okay, I have to give you an interval to find that length over. Okay, so from here, we have to figure out what is dy dx, because we're going to have to plug in that squared version into our integram there. So dy dx off to the side would be, if I use the power rule, it's going to be just x squared for the first term. And if you think of this as 4x to the negative first power, you would be able to use power rule, but you need chain rule here because of the 4x on the inside. So it would be -1 times 4x to the negative second, but then times 4 because of the chain rule. When all said and done, you would get -4 over the quantity 4x squared, which is 16x squared. And the 4/16 would reduce to -1/4 x squared, like that. So that was a lot of math kind of just talked out up here, but you guys should be able to find the derivative there with some product rule, or sorry, power rule is what I'm trying to say. Power rule and chain rule. All right, now that we know dy dx, let's plug it in. So we're finding the integral from 1 to 3 to find that length along that curve of the square root of 1 plus dy dx squared. So x squared minus 1 over 4x squared dx. Now, depending on how hard it is for us to algebraically simplify what's underneath, we may wind up defaulting in some cases once you set it up to just typing it into the calculator. I'm going to challenge us in this one to keep going algebraically and see if we can continue to break this down and be able to evaluate in the end. All right, so if I clean this up on the inside, it's going to be 1 plus, I'm going to make a common denominator here. If I multiply by 4x squared over 4x squared to make this into one fraction, 4x squared times x squared would be 4x to the 4th minus 1 all over 4x squared. So that was just kind of pulling everything into one fraction there, making a common denominator. And I think it will just make our job a little bit easier now when I go to square that. So now we have from 1 to 3, the square root of 1 plus. If I square that binomial in the numerator, you're going to get 16x to the 8th. And then you're going to get minus 2 of those 4x to the 4th, so minus 8x to the 4th with a plus 1 at the end. Over square the denominator, this is going to be 16x to the 4th. And as you're writing this, you're like, oh boy, what's happening here? But I promise it's going to get to a point where we're going to be able to do this. We've got this. Ready? Next thing I'm going to do is I'm going to make now a common denominator with that 1 plus that's out front. So this is 16x to the 4th over another 16x to the 4th. Maybe I'll squeeze that in so we can think about it like that. Okay. So if that's 16x to the 4th over 16x to the 4th, add them together, and you'll notice how this will combine with the middle term here to make it a plus 8x to the 4th. So now we get 16x to the 8th plus 8x to the 4th plus 1 up in the numerator over 16x to the 4th in the denominator. All right, and then here's the great thing. We have this radical. We have this fairly complicated looking expression underneath the radical. The numerator can be written, it's actually a perfect square. Okay, this is a perfect square trinomial. So if you were to factor that, it would be the square root of 1 to 3. It's going to be 4x to the 4th plus 1 squared up top. Okay, so the toughest thing about this is not necessarily setting up the original integrand here. It's really all about the algebraic manipulation and simplifying if I made you do this by hand, right? So factoring that down to this, 4x to the 4th plus 1 squared, now what I can do, since we have perfect squares on the top and bottom, we can evaluate this radical and sort of make the radical go away, can't we? So I'm going to bring this up over here. So we're evaluating from 1 to 3. If I take the square root, the top would be 4x to the 4th plus 1. The bottom would be 4x squared. Okay. And if you're looking at that and you're like, I'm still not really sure how I would evaluate that definite integral, why don't we break it up? Right? Why don't we go ahead and separate this into from 1 to 3. This would be 4x to the 4th over 4x squared. That's just x squared. Plus, then it would be 1 over 4x squared, which if you want to make your life easier, you can write it as 1/4 and then x to the negative 2nd. Right? Instead of putting the x squared in the bottom, let's use some anti-power rule here by calling that x to the negative 2nd. Now we can do the antiderivative and make this x cubed over 3. Then over here, if I up that by 1, that's at negative 1. Okay, so that's going to be, if I divide by negative 1 out front, negative 1/4. And if it's x to the negative 1, we can throw it back in the denominator. So x cubed over 3 minus 1 over 4x over the bounds from 1 to 3, plug in the upper bound, plug in the lower bound. In the end, when you subtract, you get that the length of this curve from 1 to 3 is 53 over 6. Okay? All right, so we have that for the length of the curve here. The last thing we're going to add on to the lesson today is thinking about, can we do this with respect to y? And we'll do some practice with finding lengths with respect to y tomorrow in class. But just so you get the idea, if we use the formula, the length from, instead of a to b, we change it from c to d, which is usually our bounds along the y-axis there. Okay, if we have a curve now, it's 1 plus dx over dy squared, right? If we're integrating with respect to y, we have to change the inside here to be dx dy squared. So just keep that in mind if we're going to find the arc length in terms of y. So we'll do a little bit more practice with that tomorrow. I'm going to encourage you to try this one. This one, just as a quick note, you definitely need a calculator for. So don't set it up and then think, uh-oh, I don't know how to do this yet, because you're right, we don't. You'll have to use the calculator to find the length of the sine wave from 0 to 2 pi. But I think it will be pretty easy once you set it up and use your calculator to do your evaluation there. The last thing I want to do is I want to go back to the beginning of today. And talk about, well, what's happening with our curve y equals x squared from 0 to 1? Because we had some predictions from earlier. Let's see if I can find those predictions that I made, and maybe you made similar ones. We said it should be like 1.57 or 1.414, somewhere in that range. Let's see if we can now use our formula to find that length. So if we think about dy dx here, dy dx is just 2x. So if I find the integral from 0 to 1, square root of 1 plus the quantity 2x squared dx. It's really as simple as that. So it's 0 to 1 of 1 plus 4x squared dx. The only thing is we don't have necessarily a method right now. We can't use u sub here because if I find du, it's going to be still a linear term with x in it, and I don't have an x somewhere else in the integrand. So let's just do this on the calculator and see what we come out to get. And hopefully it's something pretty close to one of these two approximations that I have right here. So if we do math 9 from 0 to 1, square root of 1 plus 4x squared dx. Wow, we were pretty good approximation. At least I was. I don't know. I hope you were at home too. 1.479 to 3 decimal places. So this is 1.479. So radical 2 is a decent approximation. I think pi over 2 wasn't so bad either. But now we can find that length to 3 decimal place accuracy using our new arc length formula. Okay. Pretty awesome stuff. So next time I see you in class, we'll talk about this calculator question real quick. We'll do the warm up from the beginning. And maybe I'll even approach this same question from a dy perspective with respect to y. All right, have a great rest of your day.